All right. All right, let's get started for the day. And today, once again, I want to remind everybody, if you don't have a manual, be sure to get one from Patrick here. But today we're going to begin our second module. And this is, once again, corresponds to the second chapter of the book you guys have got. And this is about radio and signals fundamentals. So what we're going to do here is kind of just lay some groundwork in this particular talk. What I'm going to do is give some basic definitions. I'm hoping for some of you who are engineers, a lot of this stuff will be very obvious because you should have seen it in a lot of your classes. But even if you're not an engineer, hopefully I'll explain it at a level where you'll be able to follow what all this is about. So, first of all, we're going to talk about radio equipment basics. Because I'm going to be using some words in the rest of this talk which you need to understand the words I'm using. For example, transmitter, receiver, and antenna. Exactly what do those mean? So, this radio, this little handheld radio, each of which you're all going to have your own copy, this radio incorporates both a transmitter and a receiver and an antenna all in the same package. And so what we're seeing here is all of this typically is going to be in your modern radio. What people will have normally is they may put up an external antenna or a separate antenna, but sometimes the antenna is incorporated. So the transmitter, it generates the signal. The transmitter is how you send your message out to everybody else. It takes a signal and then converts it into some kind of format, voice or Morse code or digital data that other people can understand and receive. The receiver flips that around. The receiver picks up that signal from over the air and then converts it into something you can understand. And we've all been using receivers our entire lives. You think about you're listening to the radio, AM or FM radio, or you're watching TV. All of that, you're receiving a signal that's being sent to you from somebody else. So the last part is the antenna. And the antenna can be separate from the transmitter and receiver, or it can be actually integral. And so in this particular case, when I look at this little thing here, that's my antenna. So the antenna can actually be separated from this. I can actually install different antennas onto this radio if I want to. In fact, I could install an antenna and run a feed line and put an antenna on the roof of this building and work off of this radio. And so when you have your own home setup, you might do exactly that. But if you want something that's small and portable and simple, you'll have a simple little antenna like this that will actually connect directly in to the radio you're carrying. Now, along with this is the transceiver. Transceiver is simply the transmitter and receiver combined together into the same package. And normally you're going to be sharing an antenna. So for example, I have only one antenna. The transmitter and receiver both use it. And so there's going to be an automatic switch inside of this transceiver unit that's going to allow the transmitter and the receiver to switch back and forth and connect to that antenna. And then finally, of course, something I didn't mention here, but there's a power supply. Radios need power. And in this case, this little radio's got a little rechargeable battery. Well, we're all used to that, right? We have to charge up our electronics. This is no different. So these little definitions, I'm sure you've probably heard the words transmitter, receiver, and antenna over the years, but in this case, I want to kind of put them in the context of ham radio, what amateur radio is about. So, first of all, we need to know about the metric system, because all engineering, just like everything else, metric system is part of how we describe things in science and technology. And so, if you've taken any type of science courses, physics, chemistry, anything at all, you've seen this. And even if you haven't, if you've ever, for example, you have computers, okay? What is a megabyte, okay? How much memory do you have? A gigabyte. Kilometers, kilograms. We've seen all these types of expressions before. So these prefixes basically give us ways of expressing numbers over very small to very large ranges. And we note that mega and giga use capital letters when they are abbreviated, so M and G. Here is a table, and this table is actually in your handbook there, or actually in your study guide. And so here is, for example, a table showing all these different prefixes and what they mean numerically. Now, along with knowing the metric system or being familiar with it, you also have to have some vocabulary to describe what a radio signal is, what a radio wave is. And so we're going to need a little vocabulary, and I'm going to spend a little time defining some terms. And again, if you've had trigonometry, what I'm going to talk about here is not that unusual. This is something, a lot of these terms will be familiar to you. So, radio signals are composed of waves of electromagnetic energy. And they can be mathematically described using sinusoids, sines and cosines. So again, if you've taken trig, you've seen these concepts before. So radio waves, they oscillate, and by that I mean they continuously vary in amplitude in a repeating sequence over time. So a radio wave repeats this pattern over and over again. One complete sinusoidal sequence is called a cycle. So this to this is a single cycle. Here is another cycle. And so, again, definitions. Now, along with this, amplitude describes the maximum magnitude of a sinusoidal wave. So the amplitude, for example, is going to be described by these peak values at the top and the bottom of the sinusoid. In addition, frequency is how many cycles that wave goes through in a second, cycles per second. Nowadays, of course, we measure this in hertz, okay, or Hz. So megahertz, gigahertz. Again, these are words you've probably heard before. So in this case, if this were, for example, 1 second from here to here, I'd go through 2 complete cycles, and I'd say it's 2 cycles per second. The period of the cycle is its duration. So in other words, how long does it require to complete 1 full cycle? So measure out a cycle, find out, measure along the time axis. How long is that? That's the period, T, capital T. And you'll also hear words harmonic and fundamental. And these are kind of be tossed around, and we'll talk more about those later. But a harmonic is a signal that is a multiple of another signal. So for example, I've got one signal here, one sinusoid. I've got a fundamental frequency. Here I've got harmonics of twice and 3 times that fundamental frequency. And it turns out a lot of radio gear operates on the idea of generating harmonics. Okay? That's how you can get a higher frequency from a lower frequency, is by, in effect, doing frequency multiplication. So you will hear these types of terms and see these. And we're going to see all this again, but once again, I'm just right now establishing definitions. So, more vocabulary. Phase. You'll hear the word phase tossed around. Now, this is expressed in degrees. And it's a way of comparing 2 sinusoids and, in effect, seeing how they are aligned in time with respect to each other. So, remember that a sinusoid, if you remember your trig, you go through 1 complete cycle of a sine or a cosine wave over 360 degrees. So again, if you had your high school trig, you remember that. So in this case, let's say we're comparing 2 sinusoids. If I shift one of them with respect to the other, I can measure that amount of shift in degrees, in how much of a fraction of a cycle. So in this case, here's a quarter cycle, which is 90 degrees. Here is half of a cycle, 180 degrees. And so I can say that I've got 2 waveforms that are 90 degrees out of phase with each other, and 2 waveforms that are 180 degrees out of phase. Or I can say I've got a 90 degrees phase shift or 180 degrees phase shift between those 2. So it turns out there are a lot of interesting modulation schemes and transmission techniques that are built along the concept of phase. Now let's talk about electromagnetic waves. So electromagnetic waves are composed of electric and magnetic energy fields. That's why we call them electromagnetic. They vary in the pattern of the sine wave. So once again, we describe how they behave with sinusoids, as we talked about before. They travel at the speed of light. So all radio waves, all electromagnetic phenomena travel at the speed of light. And signals from a radio transmitter cause the electrons in an antenna to move, which in effect basically results in the generation of electromagnetic waves. So in other words, when I talk on the radio, my transmitter is generating an electric signal which goes into the antenna, and the antenna then generates an electromagnetic wave which other people can hear. And the same process works in reverse. So if I am listening, I'm receiving on my radio and listening on it, I'll be picking up electromagnetic waves sent out by other transmitters, and they in turn will cause electrons to move within that antenna, and that converts to an electric signal that my radio, my receiver, can then pick up. So when we look at how radio works, you have to understand the concept of the frequency spectrum. So the electromagnetic spectrum is divided into different ranges according to frequency. And so here we kind of show sort of a very large range of frequencies. And this is kind of a logarithmic progression here. So factor of 10, 3 kilohertz, okay, to 30, to 300, 3 megahertz, 30 megahertz, 300 megahertz, all the way up to 300 gigahertz. So we go from very low frequencies to very high frequencies. And this range from about 20 kilohertz to about 300, several hundred gigahertz, this is considered or called the radio frequency or RF spectrum. Now, I want to say, however, although normally we define this starting at 20 kilohertz, you can actually generate radio waves at even lower frequencies, and people have done that in the past, and we'll talk about that in just a moment. So, amateur radio, we have pieces of the spectrum allocated in just about every one of these little blocks I'm showing you here. But not just that, but other services too. So for example, AM radio has a segment of frequencies that's allocated to it by the FCC that they can broadcast in. And then TV, FM radio, mobile phones. So all the different commercial services we have utilize pieces of the spectrum. And in addition, which are not shown here, military, government users use chunks of this. But amateur radio operators, we have our little chunks in here as well, and we'll look at some of those later on. So, one of the things the FCC does is to allocate how this frequency spectrum can be used. Because here's the problem with the radio spectrum. Everybody can hear the spectrum. Problem is we have to share it. And some of the signals at some of these frequencies can propagate over the entire world. So it's important that we coordinate not just locally, but also international with some of these frequencies. Because otherwise, if everybody tries to use them at once, nobody can use them. We'll all interfere with each other. So in this case, what we have here is a frequency spectrum that is controlled by government agencies in order to basically maximize the utility or the use between all the parties. Now, here are the different names that are given to the RF spectrum. Okay, very low frequency VLF, low frequency LF, all the way through MF, HF, medium high, very high, ultra high, super high, extremely high frequency. So each of these frequency ranges, RF energy, radio frequency waves, behave differently. And so you'll find that these ranges are typically split up in terms of how the RF waves or the radio frequency waves reflect or penetrate or propagate. So how easy are they to listen to? And so depending upon the frequency, we'll see different properties. So for example, up here, SHF and EHF, those kinds of frequencies tend to be very much line of sight. VHF, UHF, also largely line of sight, but around VHF, we start to see signals that can actually propagate in other ways. In high frequency, what we call shortwave, those signals can actually bounce through the ionosphere. They can transmit for hundreds or even thousands of miles. And then we've got, as we go down lower frequency, we've got signals that in effect travel along the ground, so to speak, or what we call a ground wave, and they go hundreds of miles. And the range, it's a trade-off in terms of range versus reliability. So sometimes, for example, in shortwave, you can travel enormous distances when you transmit, but the signal path is not always reliable. You can't always be sure it will work. On the other hand, on these lower frequencies and medium frequencies, you may not necessarily have as much range, but you'll always have a very reliable signal. So, I mean, for example, AM radio. When you listen to the AM radio, you turn it on, you expect to hear the radio. It's very, very rarely that you're not going to hear a good, strong AM signal from a station that's, a couple hundred miles away. So FM radio, you can typically hear a good signal maybe 40 or 50 miles away. So you're trading off, in this respect, you're trading off reliability for range in some respects. So we'll talk more about these, okay? Obviously, amateur radio operators use these different frequencies, which means we have to have equipment and antennas and transmitters and receivers that are optimized for the use in these. Now, when you look at how the spectrum works, when we've got a receiver, you can tune across a portion of the spectrum and tune in and listen to different signals. So for example, here's the AM band. If you actually are turning and tuning the radio, you will hear how you will get points where you get a nice strong signal and you clearly hear the signal. As you keep tuning the receiver, it gets garbled and gets weak and then drops out completely and you hear nothing but noise until you hit the next strong signal. So this is what receivers do. Receivers are selective. They let you tune in on one particular signal that you want to listen to. And we'll talk a little more about that as well later. So this is basically just a little example, something you all can kind of mentally think of. You think about AM and FM radio, okay, how you can tune in and listen to one signal only. Wavelength, we should also talk about. Wavelength is the distance that a radio wave travels during one cycle. So looking at this sinusoid, if I were to measure the distance, okay, if I were to think about that radio wave, I could make it visible and I could see it. I could actually measure the length of a sinusoid that one wave goes through. And so wavelength, we define that with a symbol called lambda. And since those radio waves travel at the speed of light, it turns out that we can basically describe a frequency or a particular set of frequencies in terms of the bandwidth, okay, or I should say the wavelength, I'm sorry. So for example, a ham radio operator may refer to a particular band by frequency. You can say, oh, I'm operating around 50 megahertz. Or you may describe that range of frequencies by the wavelength. You'll say, oh, I'm on 6 meters. And it turns out, of course, that lambda equals C over F describes the relationship between lambda, wavelength, and frequency of the radio wave. Because C, the speed of light, is constant. And so, for example, I can say 144 megahertz I'm operating at, or I'm operating at 2 meters. And so, knowing the speed of light for a radio wave, I can always go back and forth between frequency or wavelength. And you notice also from this formula, the higher the frequency, the shorter the wavelength, and vice versa. So as you go higher in frequency, the wavelengths get smaller. As you go lower, they get longer. All right? So that really basically covers most of our fundamental concepts. Now what I want to do is spend a little bit of time going over some of the questions you'll see in the book that relate to these concepts we just talked about. So let me switch over here. Okay, so here are some questions from the book. Let's kind of go through. And these cover some of the stuff we just finished talking about. Every one of these questions is in the back of the book. You may see one of these questions on your test. Again, the questions that you're going to get are going to be randomly drawn out of that question pool that's in the back of the study guide. So for example, how many milliamps is 1.5 amperes? It is C, as a matter of fact. What's equal to 1.5 million hertz? What's that equal to? A, 1,500 kilohertz, correct. What's equal to 1 kilovolt? C, 1,000 volts, correct. So that right there is the answer. What's equal to 1 microvolt? A millionth of a volt. Okay. Now, guys, you could go through and memorize all these questions, but I hope if you've got a science background, you will know how to do this, okay? So, like I said, some questions you might have to memorize, but some questions you can figure out from first principles if you know the background. What's equal to 500 milliwatts? Half a watt, B, right? 3,000 milliamps. D. Okay, 3.525 megahertz. No, it's C. You had it right the first time. Okay. All right. Okay, 1 million picofarads. Well, picofarad's 10 to the minus 12. It's B. All right. Okay. Now see, this is where you want to know the geometric prefixes, right? All right. What's equal to 28,400 kilohertz? D is correct. All right. What's equal to 2,425 megahertz? Correct. C. What's the unit of frequency? Hertz. Oh, B, Henry, is for inductance. Okay. Is your name Henry? All right. All right. So, what describes the number of times per second that an alternating current makes a complete cycle? Frequency, correct. Okay, so you guys are getting all these right. All right. It's not that hard to get your license. A lot of this stuff is very fundamental. What's the abbreviation for megahertz? It is incorrect. D, yes. Because hertz is capital HZ and then the capital M goes on the front. Although you'll see a lot of people misspell it and do that. All right. What's the abbreviation for kilohertz? Okay. Correct. What frequency range is referred to as VHF? It was a very high frequency. What range was that?
I'll go B.
You are correct. You are correct. It is B. You are absolutely correct. What frequency range is referred to as UHF? Ultra high frequency.
C.
D. D, yeah. No, it was megahertz versus kilohertz, okay? Yeah. What frequency range is referred to as HF, high frequency, sometimes called shortwave?
B.
C, okay. 3 to 30 megahertz, okay. So once again, read the book, take the tests, and some of these you'll just know by heart very quickly. Okay, what does the abbreviation RF mean? It is indeed A, correct. What's the velocity of a radio wave traveling through free space? I hope everybody would know it's the speed of light. What's the relationship between wavelength and frequency? It is in fact B, yes. So they're inverse to each other. Longer wavelength, shorter frequency, vice versa. What's the formula for converting frequency to approximate wavelength in meters? And that was actually in one of the diagrams. I didn't go over it, but did anybody spot it?
300 over, wait. C.
It's D. Wavelength is 300 divided by frequency. Okay. So wavelength and frequency are inversely proportional. So wavelength will be something divided by frequency, or frequency will be something divided by wavelength. In addition to frequency, which of the following is used to identify amateur radio bands? So besides frequency, how do we describe radio bands? Yeah. Wavelength in meters. Yeah. 20 meters, 40 meters, 80 meters, 2 meters. You'll hear a ham say that all the time. You'll be saying it yourself by the time you're a ham. What's the approximate velocity of a radio wave in free space? And some of you might just know that from physics. B, correct. What's a transceiver?
Oh, yeah.
A, okay. All right. that's it, guys. This second module is not too difficult, okay? Most of you, like I said, if you've got an engineering or science background, most of this stuff is really easy. You should be able to go through it pretty easily, pretty quickly. All right, so that's it for today's module, okay? Once again, I want to emphasize to you guys, if you know somebody else who wants to get their amateur radio license, please invite them over. I'll be posting this recording here up on YouTube, so you can send people over to it, they can watch it, they can realize what they're missing, and they'll decide, I want to come and get my amateur radio license. So believe me, we have plenty of manuals, we're going to have plenty of radios. So I'm going to have radios to hand out to you guys the next class we have, which is after Thanksgiving, Wednesday after Thanksgiving. Now these radios, you can listen on them, you will not be able to transmit. Transmit is disabled, but once you get your license, I'll enable the transmit on those, okay? Any questions? Because we got a little bit of time left. Anybody have any questions they want to ask? Everybody satisfied so far? Okay, good. All right, so next time we will, let's see, what is our next module going to be in? What's the next chapter? What's chapter 3? Okay, yes. So in this case, next time we're going to be talking about electrical components. So if you're an electrical engineer and you've taken electronics, this stuff will be easy. Or if you've had circuits. On the other hand, if you're not, it'll be a little more challenging, but once again, we'll try to keep it at a level where it's pretty straightforward for everybody. Okay? Anything else, guys? All right. I will see you in 2 weeks for Module 3.